In this video, the first video in Chapter 3, we'll be discussing the second building block of chemical reaction engineering. Recalling that the first building block we looked at were mole balances, and we also looked at some sizing of CSTRs, batch, and PFR reactors. And we also looked at the conversion for reactors in a series. The second building block will include rate laws, reaction orders, the Arrhenius equation, activation energy, and we'll also go over some high-level analysis of the effect of temperature on chemical reaction engineering. But we'll start with looking at a review of what we've previously covered. Recalling that the conversion of a species is the amount of that species that has reacted divided by the amount initially fed into the reactor, and that the mole balances we've derived for batch, CSTR, PFR, and PBR reactors are shown here. We have both the differential forms, the algebraic forms, and then where applicable, when we have just a differential form, such as the batch, PFR, and PBR reactors, we then can integrate it and get our integral forms. You may want to take a few moments to recall and familiarize yourself with these if you have not done so already. Let's move on to rate laws. We'd like to get our rate of disappearance of A, which is minus RA, as a function of conversion x. There are two steps to get there. Step 1 is the rate law, where we get our rate of disappearance of A as a function of concentrations of different species. I'll be covering that today, and then in subsequent lectures we'll be going over some stoichiometry where we'll be able to derive the concentration of species as a function of conversion. After we've gone through that, we'll be able to combine those two steps to get our goal, the rate of disappearance of A, as a function of conversion, x. But first, rate laws. This is a common model that we'll see, a power law model, where we have the rate of disappearance of A is equal to a rate coefficient, K sub A, multiplied by the concentration of A raised to the alpha power, multiplied by the concentration of B raised to the beta power. So if we had a reaction such that A plus B goes to C, this might be the forward rate law for this reaction. We say that this rate law is alpha order in A, beta order in B, and the overall reaction order, N, is equal to the sum of alpha plus beta. An important subcase that we'll examine are elementary rate laws. An elementary rate law happens if the reaction order just happened to agree with the stoichiometric coefficients for the reaction as written. For example, in the reaction 2A plus B goes to 3C, an elementary rate law would be the rate of disappearance of A is equal to the rate coefficient times the concentration of A to the second power, since the stoichiometric coefficient on A is 2, multiplied by the concentration of B raised to the first power, which is because the coefficient of B in the reaction is 1. So this would be second order in A, first order in B, and overall third order. We can also write our rate laws relative to other species as opposed to just writing them with relation to the disappearance of species A. For example, using the same equation, 2A plus B goes to 3C, we could look at it with respect to the rate of disappearance of species B. Then, instead of the one we've already derived, what we'll have as our rate law is that the rate of disappearance of B is equal to K sub B this time, and then CA squared times CB. Similarly, we can look at this for species C, but instead of the rate of disappearance of C, we'll have the rate of formation of C, which is positive R sub C, equal to K sub C, and then again times CA squared times CB. An important thing to note about rate laws is that they must be determined experimentally. We can't just assume that a rate law is elementary. Taking our same reaction, we might conceivably have a non-elementary rate law such that it is second order in A, zero order in B, and overall second order, which then would change our rate laws to depend no longer on the concentration of B, but exclusively on the squared concentration of A, as shown here. In this table, you can see examples of real-life rate laws. In the first segment, A, we can see first-order rate laws with some equations and their correspondent rate laws to the right. In part B, we can see second-order rate laws, and in part C, we can see several examples of non-elementary rate laws. Another important concept we'd like to talk about when speaking about rate laws is how to relate the rate of disappearance of A and B to the rate of formation of C and D. If we have the reaction A plus B goes to C plus D, and the stoichiometric coefficients are the lowercase letters corresponding to the species, we can look at the relative rates of reaction with a two-step process. First, we'd like to put it all in terms of 1A. So dividing out all terms by lowercase a will get us a reaction equation in terms of capital A, as seen here. From here, we can recognize that the rate of formation of A divided by the negative stoichiometric coefficient of A is equal to the rate of formation of B divided by the negative stoichiometric coefficient of B. It's important to keep track of signs here, and you'll note that we always use a negative when the species is in the reactant and a positive when the species is in the product. So in this case, we have the rate of formation of A over minus A is equal to the rate of formation of B over minus B is equal to the rate of formation of C over positive C is equal to the rate of formation of D over positive D. And this is a way that we can quickly compare the relative rates of reaction when dealing with rate laws. To illustrate this point, let's look at the chemical reaction equation 2A plus B goes to 3C. If our rate of disappearance of A is 10 moles per decimeter cubed per second, then we'll look at the rate of formation of A over minus 2, which is the stoichiometric coefficient of A, is equal to the rate of formation of B over minus 1, which is as 1 is the stoichiometric coefficient of B, is equal to the rate of formation of C over 3. And that's positive 3 since C is in the products formed. Rearranging, we can see that the rate of disappearance of B, RB, is equal to the negative rate of formation of A, or the rate of disappearance of A, over 2. Thus, we have 10 moles per decimeter cubed per second divided by 2 is equal to 5 moles per decimeter cubed per second. In a similar process, we can see that the rate of formation of C is equal to 3/2 times the rate of disappearance of A, which is equal to 15 moles per decimeter cubed per second. Lastly, we'll talk about our reversible elementary reactions. If we have the reaction A plus 2B reversibly goes to 3C, then we'll start simply by writing our forward rate law of minus RA equals K sub A times CA squared times CB. But now we'll want to think about it in the reverse direction, which is to say that 3C goes to A plus 2B. In this case, what is the elementary rate law? Our reverse coefficient is going to be K sub minus A to denote the reverse direction. And then we'll have that our A, the formation of A, is equal to K sub minus A times the concentration of C to the third power. Since we're talking about this in terms of the rate of disappearance of A, we'll simply add a negative sign to both sides. Thus, we have that our reversible elementary rate law is minus R sub A, which is the rate of disappearance of A, is equal to K sub A times Ca squared times Cb minus K sub minus A times the concentration of C cubed. By defining a new term, the equilibrium rate coefficient, capital K sub E, equal to our forward rate coefficient, Ka, over our reverse rate coefficient, K sub minus A, we can simplify our reversible rate law with the following. By pulling out a Ka, we have now that the rate of disappearance of A is equal to K sub A multiplied by the quantity Ca squared times Cb minus C sub C cubed over K sub A over K sub minus A, which is just capital K sub E, which gets us this. And this is our final rate law for a reversible elementary reaction. Now, one last thing we'd like to talk about are the units of the specific reaction rate constant, K. For this reaction, we know that the rate of disappearance of A is going to be moles per decimeter cubed per second. And as always, we know that our concentration is going to be moles over decimeters cubed. Then, knowing our rate law, we can compute what our units are going to be. Using simply a unit check, we have moles per decimeter cubed per second in the numerator, and then we have moles per decimeter cubed times moles per decimeter cubed squared in the denominator. Simplifying this out, we get decimeters to the 6th power over moles squared times second. This will bring us to the end of our first lecture of Chapter 3. I'd like to once again remind you of the sequential nature of chemical reaction engineering. So far, we've covered mole balances and a bit of rate laws, and next we'll be moving on to stoichiometry. But as we solve more and more complex problems, if you don't have a solid grasp of mole balances and rate laws, then as we add in stoichiometry, isothermal design, and finally heat effects, you're going to have a much harder time solving out the tougher problems. Thus, it's important to review and continue to make sure you have a great grasp on all the topics we've considered to this point.